Hi, my name is Margaret Johnson. I'm a sophomore from Houston, Texas, majoring in biochemistry, and my significant contribution this semester has been my research that I've done with Dr. David Nikles in the chemistry department. One of the things we've been working on is addressing the negative side effects of chemotherapy. As you probably know, chemotherapy attacks rapidly dividing cells in the body, which is great, and it attacks the cancer cells, but it also attacks things like hair follicles, digestive tract, beneficial rapidly dividing cells in the body. So we want to try and minimize its attack on healthy cells. And the way we are doing this is through a nanoscale drug delivery system for the chemotherapy. The general structure of this delivery system is a micelle compound, which is composed of a copolymer external shell that forms then a crystalline matrix to the interior. And within this crystalline matrix is doxorubicin, which is a chemotherapy drug that we're using in our research. And then in the very center is a magnetite particle. This magnetite particle functions as the switch. When we use radio frequency to heat up the magnetite particles, it actually undergoes a spin flip, and that transition of its spin flip causes the magnetite particles to heat up, and that heat actually breaks down the structure of the copolymers. And when it does that, this allows the doxorubicin to seep out of the micelle compound into the surrounding areas. So then what we do with this micelle compound is our partners at UAB have developed a targeting molecule for cancer, certain cancer cells. And so what we do is we attach this targeting molecule to the micelle compound. And then when we inject it into the body and it travels through the bloodstream, when it comes into contact with a cancer cell, this targeting molecule attaches to the cancer cell and binds it there. So that when we treat the patient with the radio frequency and cause the structure to break down and release the drug, then it's only in the vicinity of cancer cells. So this would virtually eliminate the negative side effects of chemotherapy. So one of the things that I've been working on this semester, I've been researching with him for a year. The first semester I worked on developing the attachment of the targeting molecule to the micelle compound. But this year I've had the opportunity to kind of break away and work on my own, which has been a very valuable learning experience. What I've been working on is these things called quantum dots. Quantum dots are a cadmium-selenium mixture that undergo temperature-dependent molecular fluorescence. So really what it is a way that we can measure temperature on the nanoscale. So one of the questions we have is when we treat the magnetite particle with radio frequency, how hot does it really get? Because there's a difference between measuring the solvent temperature and actually in the very core of the micelle compound where the magnetite particle is, how hot it's getting there. And we need to know specifically how hot it is there. So the way we're going to try and do this is through the use of quantum dots. And so this semester I've been working on developing the temperature gradient for the quantum dot. So I've started at a base temperature of 20 degrees Celsius and increased every 5 degrees Celsius, measuring the molecular fluorescence to determine its increase in molecular fluorescence per degree Celsius. And so now that we have that information from this semester, next semester what I'll be working on is developing a procedure to attach the quantum dots to the magnetite particles, because then we can use the quantum dots as a thermometer based on its fluorescence to determine how hot the magnetite particle is. And so one of the things that I've really loved about this project, and especially are looking forward to next semester, is my ability to work on my own and kind of develop a greater understanding of chemistry outside of the classroom. So being able to take all the things I learned in the classroom, but use it for something very hands-on and very independent. And so that's one of the things I've really enjoyed. And I'm really looking forward to next year and developing. I've been working on a lot of literature reviews, trying to figure out what previous people have done with quantum dots to determine what we can do in the future. And that's been really fun to kind of enter the research world hands-on. And so that's really been my significant contribution for this semester. Thanks for listening.